A warm welcome to all of you to the program organized by Mahatma Gandhi College, Iridi. Respected Chief Guest and today's resource person, Professor Balad Krishna Kumar sir, Dr. Ajidavi, Principal of Mahatma Gandhi College, Iridi, my dear friends, colleagues and students from various parts of the country. We all know that Mahatma Gandhi College Iridi is organizing a platform titled Learn from Professor V. Krishna Kumar, in which all the participants will get an opportunity to interact with Professor V. Krishna Kumar sir. We will also give a platform to discuss among the participants also. Today is an auspicious day for all the mathematics community because today we are going to view the inauguration of the continuous lecture program Learn from Professor V. Krishna Kumar sir. Let me introduce Professor V. Krishna Kumar sir. He is a familiar person to most of us, but it is my duty to introduce him to the audience. It will be interesting to know that he is a person having more than 45 years of teaching experience. Also, students will be get motivated to know that 50 years back, when there was only one university in Kerala, Professor Krishna sir completed his BSc from St. Joseph's College, Kozhikode, with the first rank in Kerala state. Later he joined at IIT Madras from where he completed his MSc. Later he joined at IIT Kharagpur and under the guidance of famous mathematician Professor Jyoti Das, he completed his PhD. Later he did his postdoctoral works at UK and Germany. He has more than 20 papers, research papers in international journals, well-reputed international journals, and also he supervised 2 PhDs. He has been associated with the Mathematics Talent Search Nurturing Program, MTTS and NP, for the last 20 years. And that is a program molding young minds to the world of higher mathematics. And it is very important to note that such a wonderful program molded so many persons. Those who are now in the well-reputed institutions now are once students in the MTTS and NP program. Actually, Professor Krishna Kumar sir introduced such a program in University of Calicut 15 years back, and thereby helping the students of Kerala also to get the benefit of such a program. And also, I would like to mention that 2 of his students, one is Professor Sandeep from TFR Bangalore and Professor Anand from IIT Bombay, got Shanti Swarup Bhatnagar Awards for Best Scientist. Also, Professor Krishna Kumar sir also got the Best Teacher Award, INSA, Indian National Science Academy Award in 2015 for Best Higher Education Mathematics Professor. Let me invite him for this program. He has a teaching experience of more than 45 years in which includes the service at Department of Mathematics, University of Calicut, where he served as professor as well as the head of the department for many years. Later he joined at Amrita Vishwavidyapitham, Kollam, and later he went to NISER, Bhubaneswar, where he served NISER students for many years. Later he joined at Kerala School of Mathematics, Kozhikode. Now it is a boon for all of us that he has created a studio in his home so that every week 3 to 4 lectures are telecasted through Google stream, Google YouTube stream, so that all of us will get higher level, high class lecture. Also, we are fortunate that the mathematics department of Mahatma Gandhi College is very fortunate that he is our mentor. He guided us and he motivated us to conduct a program for the well-being of the mathematics community. We are very happy to organize such a program. On behalf of all the participants in this program, I give a warm welcome to Professor Krishna, sir. Also, I wish to mention that Dr. Ajitavi, who is also a student of Professor Krishna sir. I am also a student of Professor Krishna sir, and Hasina Miss, who is also working in the Department of Mathematics, is also a student of Professor Krishna sir. Actually, our principal guided us in such a way that in order to get this program into the realization, her contribution is very much applaudable. So I welcome Dr. Ajitavi to this function. I also welcome all my friends, students, and faculty members from various institutions to this program. I also use this opportunity to thank all the well-wishers who supported us through various ways to conduct this program. Once again, I welcome each one of you to this program, and also I welcome our principal, Dr. Ajitavi, to inaugurate this function. Thank you.
Respected Dr. V. Krishna Kumar, Dr. Bijumon R, our IQAC coordinator, Sri Pramod Kumar KV, my dear colleagues and other distinguished faculties from various colleges, and my dear students. First of all, let me say how pleased I am to see so many of you joined here today morning. Actually, your presence here is a reflection of your interest in this webinar, leading by our most respected sir, Dr. V. Krishna Kumar, former head of the Department of Mathematics, University of Calicut. Among us, there are students and faculties, and I am convinced that the presence of all of you will make this webinar a highly informative and fruitful session. As you know, these types of webinars' role is to make aware the participants some mathematical notions which are not taught in the standard courses. I hope today's session will be very useful for doing research and faculties enhancing teaching. So I congratulate all the faculties of the Department of Mathematics of our college, especially Dr. Bijumana, the head of the department, for taking so much effort for arranging this webinar for you. Now, I think I have already spoken for too long. So without further delay, I will give the floor to my teacher. Sorry, our teacher, Dr. V. Krishna Kumar. I am sure that you will feel prosperous by the knowledge you received after this webinar. So, before concluding my words, with your permission, I declared that the two programs, the continuous lecture series learned from Professor V. Krishna Kumar and the webinar on Supremum and Infimum of subsets of R were inaugurated. With this, I wish a good academic session for all of you. Expecting your sincere cooperation and support, I am stopping now. Thank you.
Thank you, Ajita Miss. Dear participants, there are more than 450 participants for this program, but due to the restriction, we have only the facility to accommodate only 100 participants in this Google live stream. So we now switch over to the YouTube channel of Professor Krishna Kumar sir, Krishna's Classroom. The link is already provided in the Google Meet and also through the WhatsApp group in which you are just added. So please switch over to YouTube live stream so that we will get more than 450 persons will get the words of Professor Krishna Kumar sir, and also he will deliver a lecture on the topic Supremum and Infimum of subsets of the real line. And also, I request each one of you to come back again to this platform, this Google Meet platform, immediately after the conclusion of the lecture by Professor Krishna sir, so that we will get a facility to interact with the Professor Krishna sir. As in the YouTube channel, it will be difficult for us to interact with him. Only chatting is allowed in the YouTube channel. We cannot have a verbal interaction with Krishna Kumar sir. So I request all of you to come back to this medium immediately after the lecture. He is a very friendly person. All of you can interact with him without any inhibition. I request each one of you to come back. Now please join to the YouTube live stream. I also request Professor Krishna sir to engage in the session, and very, very best wishes to you, sir, to have a very informative session. Thank you, sir. Thank you.
Thank you very much. I'll join soon the classroom, Krishna's classroom. It's already on, and now I'll be talking to you before the lecture for a couple of minutes. And thank you for this nice inaugural session. I'll join in a minute or two.
Okay, sir.
By that time, let all the people join this.
So, good morning, everyone. Welcome to you all to Krishna's classroom. And thank you all for joining me. And then, of course, I should thank the UT College, that is MG College at UT, for organizing this webinar and giving me an opportunity to speak to you. Since undergraduate students are also there, I have chosen the topic Supremum and Infimum for this opening meet. I think it's slightly difficult concept that often people find difficult to grasp the ideas. It's mainly because of the fascinating structure that R has, that is the real line has. So we start with I'll be exploring a few things like say defining the concept of supremum and infimum of subsets of R. Then a few words about Q and why R was constructed. And then a few things that you already know, that the square root of 2 is not a rational number, therefore there exists no x in Q with the property that x square is equal to 2. Now this inadequacy was circumvented by the so-called completion process of R. Of Q to get what we call the real line R. In fact, an elaborate discussion on this, the construction of R, starting from the Piano's axioms, and then systematically building up Q first, and then going over to the construction of R using the so-called Dedekind cuts is done in this channel, that is Krishna's classroom, and it is available on the YouTube. So all those who are interested can look into it. There are about 18 episodes which has been recorded and made public. So if you systematically spend some time, it will be really worthwhile to see how R is constructed out of Q and what are the inadequacies of Q to go for R. So we will just start with the basic properties of Q. So we have Q is an order. What do I mean by that? See, Q has three structures coming out of operations. One is addition, multiplication, and then order structure. So it is Q with these three operations. Now this is a binary operation, this is also a binary operation, and there is an order structure on that. All this can be systematically brought in starting from the Peano's axioms, as you can see in those lectures. Now, one of the shortcomings of Q was that, or at least initially it was felt that it completely occupies the so-called real line. That is, on a line, if you choose a point 0 and unit 1, then you see that all the points can be possibly expressed as a rational number. I mean, this was the expectation. But to the surprise that it was found that a root 2 is something, a point on this which can be constructed using a ruler and compass, and there is a construction which you can do geometrically through a finite number of steps. Therefore, that is an achievable thing. But it was soon realized that square root of 2 has no place in Q. In fact, you see that there are more numbers of this kind, namely square root of 3 is there, square root of 5 is there, square root of 7 is there, and so on. A number of such numbers. Apart from that, you have this one of the most elegant numbers that you have called pi and e. They were also not rational numbers. In fact, it is quite a job to prove that pi is not rational, e is not rational. In fact, one proves that pi is transcendental, e is transcendental. These are very basic works in mathematics. They are not rational numbers. So it is found that plenty of them are there. Then of course you ask how big is this class? Then it was found that this class of non-rationals is much larger than the rational numbers. In fact, the rational numbers, the real line is extremely porous line. Porous line means there are plenty of holes there. Okay, and it's a huge class of non-rationals points than the actual rational class. So this is something about the cardinality of these two sets. And of course, we will just get a glimpse of some of these things. Now we see that square root of 2 cannot be represented as a rational. And this is probably where you come across very early on one of the techniques that mathematics often uses to prove results. And this is called reductio ad absurdum. Now, when the proof goes like this, suppose there exists a rational number R which is of the form P by Q, where P and Q are integers with Q not equal to 0. We also assume that we have chosen P and Q such that there is the common divisor of P and Q is equal to 1, by which you mean 1 by 3 is of this kind. But if you take 2 by 6, there is a common divisor. So you don't take the P R in the form 2 by 6 but as 1 by 3. Okay, so there is a sort of, after taking out the common factors, integer factors, whatever you get is what you say. So this is, put it this way, common divisor is equal to. Now suppose I have not completed the sentence, that means such that R square equal to 2. Then it leads to a contradiction. So you know the proof of this one, you can immediately get that P square equal to 2 Q square, which in turn tells you that P square is even, which implies P square even, and P square even implies P is even. All these needs, there you need a proof, and this is, so let me just isolate this part. P square even implies P is even. Just put here. How do you prove this? So there are only two possibilities, either P is even or P is not even. Which P, say P is odd. Oh, of course, P and Q cannot be 0, of course, right? Then what do you have? So to prove this, what you prove is that, see, this is something like two statements. Suppose there is a statement P, there is a statement Q. Now if you want to prove P implies Q, okay, so it is equivalent to saying that not Q implies not P. And so what is not, see, P is even is the statement that you are talking about. So not P even, it means P is odd. So we want to, you can actually show that if P is odd, then you want to conclude that P square is odd. How do you do that? Suppose P is odd. So P is then of the form 2n minus 1. So what about P square? P square is 4n square minus 2 4n plus 1. Now look at this. This is a multiple of 4. Okay, therefore this is even. So even plus 1 is an odd one. So that is how you prove it. So you see that at every stage you need a proof. I mean, this is something that I want to impress upon you. Therefore you prove that if P is odd, now this here P and Q stand for statements. So I'll just take it out. So don't confuse with it. Okay. So if P is odd, that means P square is odd. Therefore, if P square is even, then that implies P is even. Okay. So you get P square is even. Therefore, P is even. Therefore, what about P? P can be twice some integer n. If so, you get 4 n square equal to 2 q square. So you see that taking out the common factor, so you see that 2n square equal to q square. So q square is even. If q square is even, then by the similar argument it follows that q is even. What does it mean? even, P is even, Q is even, and therefore 2 is a common factor. Therefore, you can, what we have assumed that there is no common divisor, or P, the common divisor of P and Q is equal to 1. So this contradicts that. Okay? So this means two divides P, 2 divides Q. Whereas we have said that so 2 is a common divisor. Therefore, you see that contradicts our initial assumption. So you see that it leads to a contradiction. Okay. So let me, and hence we conclude that there does not exist a rational number with the property that the square is equal to 2. So this proof that you would have seen very early in your, maybe at plus 2 level, one of the early sophisticated proofs that you come across. Now let me therefore what we are going to do is put in all those elements which are missing. How do we do that? So we take R as the completion of what do you mean by that? That means all these missing holes we bring in, and then you can show that it gels very well with Q. You can extend the structure, addition, multiplication, and order structure. Okay? So we have Q completely embedded in R with all the structures in it. But the QR has the additional property that it is complete in the sense what? So we have to first make these things clear. So this means the following, that each bounded subset of has a bounded above, so we can write here above. Or if you remove this, then it is a supremum and an infimum. So this is what we want to do. So before that, we should know what exactly you mean by supremum and infimum. So let us define this for definition. Let S be a non-empty subset of R. We say that the first property, S is said to be bounded above if there exists a U belonging to R such that S is less than or equal to U for every S belonging to S. That's quite Then of course U is called, U is then called an upper bound now. Yes. Now what we have is, if you consider R, there are bounded sets as well as unbounded sets. This sets which are bounded above, sets which are not bounded above. For instance, if you take the set of integers, that is the natural numbers, it is not bounded above. The reason is that if you take any element in it, then there is always, suppose we assume that you cannot find a number n such that all the elements in a set of natural numbers are below that. That's the reason. So it is unbounded. So also if you take the set of all positive rational numbers, it is not bounded above. Now we also define what is called the bounded below. S is said to be bounded below if there exists V belonging to R such that S is greater than or equal to V for every S belonging to S. V is called a lower bound now. For example, you take this set, say S equal to the set of all X belonging to R such that one. Now you see that 1 turns out to be an upper bound for this set, 0 turns out to be a lower bound for this set. Okay, so this set is both bounded above and bounded below. Therefore, it's a bounded set. A set that is bounded above as well as bounded below is what you call a bounded set. So this is a bounded set. Another thing that you observe is that 1 is a bound for this, 2 is a bound for this. So bound, if a set is bounded, then the bound is not unique. Okay, so there are several bounds that you can have. If n is a upper bound for the set, then n plus 1 is also an upper bound. And in fact, any number greater than n is a upper bound, and there may be or may not be something less than n also an upper bound. You do not know. Once you say something is an upper bound, there may be on something less than that also an upper bound for the given set. We do not know. We have to be working on this idea to get what is called the notion of supremum and infimum. Okay. S is bounded. S is bounded if it is bounded above and bounded below. If both these conditions are satisfied, then we say it is bounded. Otherwise, you say it is unbounded. Okay? You should take Q. Q is unbounded in R. Okay? The set of natural numbers is bounded below but not bounded above. The set of integers is unbounded. It is bounded above, it is not bounded above, it is not bounded below. So these are all some of the things you are familiar with. Right. Now let us, so we have said that if some set is bounded above or bounded below, the bound that you have is not unique. So non-uniqueness of the upper and bounds. Okay. Now we are in a position to get the best possible bounds. Suppose you have got a, suppose this is your set. Okay. This is a set. Now you see that anything over here is an upper bound. This is a boundary set. Anything over here is an upper bound. Now you see that what one would like to look at is a bound which is the least among all these upper bounds. Similarly, a lower bound which is the maximum of all these lower bounds. Okay, so this is what we are trying to work out. Okay, definitely. Let if S is bounded above, then a number U is called a supremum of if the following is true. First of all, the first property is that U should be is an upper bound of yes. So every supremum has to be an upper bound. Okay, that's the first property. It should also have the second property, namely, if V is any other upper bound of A, upper bound of S, then we should have V is okay, U is less than or equal to V. Okay. So there is no bound of S below U. This is the mean. Now, in this context, you might ask whether the supremum exists or not. Now, this is where we have brought in the concept of completion. What is the completion? See, R is a superset of Q, okay, with the property that every subset bounded above has a supremum in this sense. Okay, now you see your Q does not have this property. For that, so if you take, you know that, see, you look at this set. Later we are going to work on this. Look at this set. Now this is, we will show that this is bounded above. But as we have seen that there does not exist in Q a least upper bound for this. Well, that's the problem. Now we have constructed R from Q such that such holes have been pegged so that this set has an upper bound. Not only this set, all sets of this kind has an upper bound. In fact, every bounded subset, every subset of R bounded above has a supremum. So also every, one can easily get from it, every subset of R which is bounded below has an infimum. We have not defined what infimum is. Now we will define this. So let me define infimum. So what should be the definition of infimum? See, the infimum is, what are the conditions that we are talking about? Yes, bounded below, first of all. Then you say V is infimum of S if the following two. One, first thing is that V is a lower bound of S. Two, if W is then W is less than or equal to, okay. So V has this particular property. When you say it is V, then we say V is the infimum of S. Okay. So what one has in R is the extra facility, namely all bounded sets have both a infimum, a supremum as well as an infimum, or what you call a least upper bound and a greatest lower bound. So it must be clear from this. Supremum is also called least upper bound. And infimum is greatest so these are the terminologies that one usually uses: least upper bound and greatest lower bound, which are also called supremum and infimum. So every bounded set has a supremum, every bounded set has a infimum. In fact, every set, subset bounded above has a supremum, bounded below has an infimum. And this is precisely the property that Q does not have. You cannot say for sure that every bounded subset has a supremum. For example, we have already seen the set of all x with the property that x square is less than 2, where x is confined to Q. In that case, you see that in Q you don't have this doesn't have a supremum. Okay. Now, one of the observations is that both, so proposition the supremum and infimum whenever they exist are unique. Okay, how do you prove this? It's quite easy to see why it is so. This is just simple. Suppose S is given, bounded above, and therefore suppose U1 is a supremum, U2 is also a supremum. Okay? Then U1 and U2 are two real numbers. Okay? So you have the trichotomy. Either U1 is less than U2, or U2 is less than U1, or U1 equal to U2. So you show that both U1 less than and U2 less than U1 are not possible. Therefore, the only possibility is that U1 equal to U2. Okay? Why is it so? Suppose U1 is less than U2, then U2 is an upper bound. But that is not a least upper bound because there is U1 below that, so it doesn't satisfy the second criteria. Okay? If you interchange the role of 1 and 2, then you get the other result. So you see the only possibility is that U1 is equal to U2. Likewise, you can show that if the infimum exists, then infimum is also uniquely determined. Okay. So we have the uniqueness of the supremum and the infimum. Now one should also understand this more clearly, because in a situation you need some technique to prove it, because so there are usually in mathematics this is the practice that if you define something, then you try to get the equivalent forms of that. Okay? The equivalent forms of that means what? We should have some other result which is equivalent to this one, so that you can even replace your definition by the characterization of that definition. These are called characterizing theorems. So you have some alternative formulation. And all these require proof. I am not going to prove them, but you have to try to prove from very systematically. So we have, you know that U is an upper bound. We are now trying to get other forms bound That means this is if and only if S is less than or equal to U for every S belonging to S. Okay, so that is that. Now we have to go for the second thing. Let's see, this is only talking about the upper bound. Now we have to talk about the least upper bound. So how do you do that? Okay, let us see what all this can happen. Suppose U is the least upper bound, and as I said, there is some points, etc. They constitute the S. Okay. Now, what do you mean by this is the least upper bound? It means if you take any other upper bound V, okay, then certainly U is less than V. So U is less than any other upper bound of this. This is the meaning of what you say U is the least upper bound. Which other forms you can have? So that is one form. That is V is, if V is any other upper bound, then U is less than or equal to V. Now this is the definition that we have chosen, right? It is also equivalent to saying that if Z is some upper bound, some number which is less than U, then Z cannot be an upper bound of it. And that's what you are come to the extreme point. That's the meaning. So if Z is such that Z is less than U, then Z is not an upper bound of yes. What do you mean by that? Suppose when you say Z is not an upper bound of this, it means you can find some S1 in S such that S1 is greater than Z. Okay? So this means Z less than U, then there exists a Sn belonging to S such that Z is less than S. That's what I said. So this is your essay. So you say that this is not the least upper bound. U is the least upper bound means if you take any Z, then there is an Sn that is squeezed between these two. I will explain this now. I mean, for instance, let us take the sequence one by n. So what do you have? See, similar comments hold for, or let me take 1 minus 1 by n. Sequence 1 minus 1 by n. So what do I have? So you are starting from 0 and 0, 1 by 2, then you have 2 by 3, etc. See, one can easily prove that 1 is an upper bound. In fact, 2, 3, I mean, there are infinitely many numbers which form the upper bound for this particular set. Okay. Now what is the least upper bound? As you can see, it is going to be, I mean, you get the gut feeling that it is going to be 1. But how do you conclude this? If 1 has to be an upper bound or a least upper bound, then you have 1 minus 1 by n less than 1 for every n. I mean, that is true. That is satisfied. But what about the second condition? To be the least, you see that if you take any other number, u or z here, then you see that you can always find a number of the type 1 minus 1 by n lying between z and 1. Okay? So that is the condition. So you see that one of the things that you have to prove is that z less than u, then there exists this. Okay, a fourth this is put in a different way. It is this: if epsilon positive, then there exists S epsilon belonging to S such that u minus epsilon is less than S epsilon. So what does it say? It says the following. Suppose this is your u. So this is your S. Now you say that this is the least upper bound. Then what happens? You choose an epsilon positive. Then what you have? You take this is going to be u minus epsilon. So in between, you say that there is some number S epsilon such that u minus epsilon is less than S epsilon, and S epsilon belongs to S. That is the condition that this has to be. This has to be, the u is the least upper bound. If it is not the least upper bound, then you can always do it. Suppose you take a v, then you can find an epsilon such that none of these, there does not exist any element of this kind. Okay, between u minus epsilon, and there does not exist anything like this. So for instance, in this set, suppose you take 2 as the bound and take epsilon as half. Then you see in between 3 by 2 and 2, there does not exist any element of S. Okay, so I think you got an idea of this. But what you should do is, I don't have time because I want to prove some certain things more, precisely. And then this. So one thing that you should have, it's a good exercise that to prove the equivalence of this. For instance, assuming this, you can try to do this. Okay, so, and assuming this, you have to get back the other one. So you show that both these are equivalent. So any one of the form that appears to be most easy to verify, you can use to establish that a particular number is. And you should also look at a lavish number of examples, and then in each case find out the supremum and infimum. First locate the, see, there are two things. It's not merely locating the supremum and infimum that comes into the picture. You have to also prove it. I mean, this is something of a compulsion of mathematics. That suppose, for instance, you say that here 1 is the supremum. It's not merely go and state that, just make a statement that 1 is the supremum, but you also have to prove that this is the least upper bound. So you have to verify the other things also. Okay. So a proof has to be provided. whenever you make a statement for a particular example. So now I think I will just leave it at that. You try to construct a proof for this. Now, one of the useful results that you can have is that suppose, okay, we make a remark. The supremum as well as infimum may not be as we have seen in the examples. I mean, here, see, S consists of all those elements of the form 1 minus 1 by n, and 1 is not in it. 1 is not a member of that, but 1 happens to be the supremum. So also 0 happens to be the infimum, and of course there 0 happens to be in it. Okay, so it's not necessarily true that infimum and supremum belong to the same set. Okay. Another property that you have is that if you take a finite if S is a finitely many elements, then there exists a U and W in S such that it has both its infimum and supremum in it, and this is called the largest element, and this is called the smallest. This is true of any finite set. And one uses what's called the method of induction to prove this, because you see that if you have only exactly one element in the set, then it is obviously true. Assume that it is true for any set with k elements, then you adjoin to it one more element and then prove that it is true for when you have enhanced this collection with the additional element by making a very simple argument. Okay, right. So it is by induction that you prove this. There exists a least element. These are obvious things, but in mathematics you need a proof to ask for it. Now this is a culture that you have to accept the moment you choose to be a mathematician. Okay. Every time you have to ask questions like whether something exists, something is uniquely existing, and these kind of questions are very part and parcel of the discipline. Now you know that if you take S to be this is not empty, and you see that the supremum is equal to 1, the infimum is equal to 0. Even if you remove this, the supremum is equal to 1, the infimum is equal to 0. So these are between things. So what you call the completeness property of is something which enables you to talk about the existence of Supremum and Infimum. Okay? Suppose you are discussing this in this context, I mean, you know, the following, in the context of, that is, as I said, where you take x belonging to Q and search for the Supremum and Infimum in Q. Does it have a Supremum? But Infimum, no problem. But of course, it's when you take the whole thing, then it's a difference. Okay, right. You see that this is a set where the Supremum does not exist. So it really depends on, that's why we have completed Q to R to get R. So in R we are assuming that all bounded sets have all sets all subsets of R bounded above has from which one can prove that if a set is bounded below, then it is an infimum. Now, using some other properties, you can connect the two things together. You look at the set of all x belonging to R to S, then you construct another set minus x for x belonging to S, and then consider the relation between the Supremum and the Infimum of these two sets. That's all you do. Now one can prove little things like suppose properties. These are all again requiring proof. That is, suppose S is non-active. Then you have, let A belonging to R. Then if you define a new set called A plus S, this is what you call A plus X, where X belonging to S. All this is sensible because you are working within R, where you have addition and you have multiplication, you have an order relation, everything is there. Now you can prove that the Supremum of A plus so this is what is this set? This set is, suppose you take this as your S and you take an A positive, so you take A. What you are doing is you are moving each one of these sets through what you call this distance A. So what you have, so you have to, you get somewhere here. So A is this. Okay, so you are translating everything to the right. So this is what your S plus A. Okay, you translate everything through A. So if A is positive, you are moving right. If your A is negative, then you are moving it backwards, namely to the left. Okay, so it's a translation. So So this is something to do with the translate. Sometimes you will have to use that. Okay. Now some more properties that are rather require proof but may be obvious is that the following. Okay. So let us take two non-empty sets in R. A, B, suppose B. What does it mean? On the real line, you are considering two sets A, two sets B. So you are taking an A here, you are taking a B here, so A is less than or equal to B. In fact, this is true for every A and every B. That clearly tells that these two are at most having a just a root at a point. Otherwise, you know, if you are taking these as open sets, then they are going to be, destroyed. Then, what happens? See, what you can say, what is obvious? See, this is the upper bound, least upper bound of B. This is the least upper bound of A. So you can immediately get that supremum of A is this is obvious. Infimum of A is greater than or equal to infimum of B. Infimum of A is less than or equal to infimum of B. Then you also have supremum of A is less than or equal to infimum of B. Now this is B. And what is the infimum of B? Infimum of B is here, infimum of supremum of A is here. You see that this is C. But you have to give a proof for this. That's not difficult. I mean, it's very easy to write down a proof for that. Now one can come to the question of some functions. What suppose both, so D is a subset of, now we define two functions, F from B to R, G from B to R, two functions. And suppose Fx is less than or equal to Gx for every D. Let's take an example. What will be the nature of the graph? Suppose this is your D. So D is equal to say 0 to 1. So we are assuming Fx is less than or equal to Gx for every t. So you take an x, the value of the function f, this is your f, say, and just taking a recommended situation. G is something like this. This is Fx and this is Gx. So this is your Fx and this is your Gx. Now, what you can do is, you see, you have a set of values of Fx over x belonging to D. Or you can ask for the supremum of that. What are the values here? In this function, if you have, you take there is the upper bound and the lower bound of f. So f is a map from D to this interval. Okay. So you have the minimum and the maximum here. I mean, I am talking with reference to the figure. Now I can only talk about supremum and infimum is the bounded set. So if you are talking about bounded functions, then you have the range bounded. Okay? And then it has a supremum and an infimum. So you can talk about that. Similarly, you have got for G also the same sort of thing. And what one can prove is that supremum x belonging to D of fx is less than or equal to supremum of gx x belonging to D. Similarly, you can prove for infimum also with inequality possibility. But what you can say is that this is not necessarily true, not this one, but you cannot say that supremum of C. You would like to ask whether supremum of F x belonging to D is less than or equal to infimum of G belonging to x belonging to D. Whether this is true or not. Quite obviously it cannot be true. It need not be true. For instance, if you take the functions, I will give a graph of the functions. You take square and gx equal to x for x belonging to 0, 1. What are the graphs? It is 0, 1. This is your G. Okay? Whereas F is this. This is your F. What is the infimum of G? See, supremum of F is here 1. Clearly. Whereas infimum of G is 0. So you cannot make a statement. So this, for these functions, this is not true. Okay. So this is clearly not true. So some of the little things. So let me introduce a property called Archimedean. N is not bounded to given x belonging to R, where exists n belonging to n such that x is less than. What is the content of this one? See, this is 0, so this is 1. Now what it says is that, of course, obviously when x is negative, this is obvious. 1 has this property. But suppose x is positive, so it's somewhere here. So what it says is that by walking n steps, each step of unit length, you can just overtake this point. Okay? 2, etc. So this is some. It's a very simple, obvious thing on the real line that we talk about. This is called continuum. So let us prove this. Okay, let us look at this one. Archimedean property is then if X belongs to R, then there exists this is the property, Archimedean property that we are talking about. Now we want to prove this. Okay? I just give it. This gives an indication of how you prove such things. See, here you use the Supremum and Infimum ideas. So it's just to show how you use these ideas. Okay. Proof. Again, a contrapositive argument. What we assume is that this is not. Let's suppose what is the implication of that? The implication of that is the what does it say? This implies n is less than or equal to x for every n belonging to n. That's the negation of the other statement. Okay? N is not bounded. If n is bounded, then there is a bound called x. So this means x is an upper bound okay, and that implies what? Any subset of R having an upper bound has a least upper bound. So we are using the supremum. So there exists a supremum for n, say u belonging to R. This implies, now you see you have come to Supremum. So we have got every n is crammed here. Suppose this is the least of such bounds, then you call u. Now you take epsilon to be equal to 1. So you take u minus, take u minus 1. Okay. Then u minus 1 is smaller than u, the supremum of n, and hence u minus 1 is not an upper bound of n. So u is the least upper bound, therefore u minus 1 is not an upper bound of n. So what does this mean? This implies there exists an m belonging to n such that u minus 1 is less than n. That's the meaning. What does this mean? This implies u is less than n plus 1. Just translate inequality goes adding 1 on both sides. This implies m plus 1 belongs to n is an upper bound of and violates the assumption that U is the supremum of okay. Therefore, that completes the proof. Okay. Therefore, you see that it leads to a contradiction. Leads to a contradiction means what? The set of natural numbers is not perfect. Probability. These are important things. If S is equal to 1 by n such that n belongs to n, then infimum of S is equal to 0. I mean, that's for you to easily work it out. And you can give a proof using this, because you see that you can get a ball and then switch it back and so on. So you see that how you prove it is the following. I mean, suppose prove S is not empty. That's clear. Bounded below by 0. Now this implies an infimum. Let clearly what we have is that is greater than or equal to 0. Now for any epsilon, one by epsilon is less than n implies one by n is less than. That implies 0 less than or equal to w less than or equal to 1 by n less than. Therefore, for any n this is true. Therefore, w is equal to 0. Okay, one more result that you can prove is the following. That is that probably. Okay. If y is positive, then there exists and y, that's an integer belonging to n, such that n y minus 1 is less than or equal to y less than n1. That means any number can be squeezed between some ny integers and y and 2y plus 1. I mean, this is a very useful result. The consequence, one of the consequences of this is that 1 by y lies between 1 by ny plus 1 and 1 by ny. So 1 by y That's a consequence of that. Okay, so that's this again. You can look into all that the book by Bartle and Shepherd for the proof of it. These are important to prove these things systematically. So you should spend some time just reading through these things systematically. Find the proof of it. Now let me just make some statements about the existence of movement. I'll outline the main points that you use to prove this theorem, because the time is probably short and yet maybe this is too lengthy otherwise. Okay, let me do that. So the theorem that you have is the following. There exists a positive real number x such that x squared equal to, this is the statement. So here, if you replace this by rational, then there is no solution for this equation. Okay, but the moment you put real, this is completely based on the supremum property or the completeness of R that you have. Okay, so what you do the following. So you start with, on the real line, now you choose a set which is say, this is the set of all x with the property that x square is less than 2. So you start with that set. So this particular set, this is the set. So we start with say yes. So let us concentrate on this. Okay. Define S to be the set of all S belonging to R such that first of all, does there exist such a set? Okay, on the picture, yes, it is fine. But you have to show that it exists. So the first question that you ask is yes, you can show that 1 belongs to S. Why should 1 belong to S? Because if S is equal to 1, then 1 square is 1. 1 is less than 2, therefore it's an element of that. So this is common. So that's the first thing that you prove. The second thing that you prove is that 2S is bounded above. Well, what you use is that if you take 2, S is equal to 2, then you have S square equal to 4. Okay? Therefore, S equal to 2 is a bound for S equal to 2 is a bound for this particular set. And what you have is that S belonging to S, or S is bounded above because 2 is less than or equal to, see, this 2 is less than or equal to 2. That's what it says. So if D is greater than 2, implies D square is greater than 4, therefore D does not belong to S. Now, see, the set that we have considered is a non-empty set which is bounded above, therefore it has a least upper bound. So call that X, which exists. Why it exists? It exists because of the completion property. What we are expecting is that this particular X is going to serve the purpose. Okay, this particular X is going to be the number whose square is equal to 2. Okay, so all that we have said is we have defined it as the supremum of this. This is the definition. We do not know what it is. No idea what it is. So you see, what is that you expect? I mean, this is in mathematics, speculation becomes quite important. So we speculate that the supremum is going to serve the purpose. Okay? So what is it? So you have now 3 possibilities. What is it? We are looking for this statement, x square equal to 2. Is it true? Okay? That's the question that you are asking. So what are the possibilities? X square could be less than 2, x square could be equal to 2, or x square could be greater than 2. There are 3 possibilities. That is what at the outset, that's what you can say. Given two numbers, because of the trichotomy, either this is true, or this is true, or this is true. So we want to show that this is true, which means you have to show that this. See, you cannot have all the 3 or any pair of them simultaneously true. So what you can do is rule out these 2 possibilities so that you are left with the only choice, namely x square equal to 2. So show that is not possible. Similarly, show that is not possible. So if you show these 2 things, then you are done. Then you are left with only one possibility, namely x square equal to 2. So the supremum gives you exactly what you are asking for. The supremum exists because R is complete. Now this is the property. So you see that the 2 possibilities. So you see, if x square is less than 2, it leads to some contradiction. So also if x square is greater than 2, it leads to some contradiction. This is how you prove it. So let me just outline one of the cases and then leave the other for me. So I can say something. Okay, so assume less than 2. We've shown that x is in such a case not the supremum of S. Okay? That means no x with the property that x square less than 2 can be the supremum of S. That's what you are saying. Okay. So how do you prove that this is supremum of x? Okay. What you can do is that you can find x plus 1 by n. You show that there is an n such that x plus 1 by n belongs to S in that case. Okay, so this is x plus 1. This is in S, then what does it say? X cannot be the supremum. See, if x plus 1 by n for some n is in S, then what it says is that x plus 1 by n is greater than x, and therefore this cannot be the supremum. Okay, so we try to prove that. So we try to find out such an n under the assumption that x square is less than 3. Okay, so let us show that such an n exists. So how to that? For that, what you do? So you see, you take x plus 1 by n. So claim that exists n is that contradicting the supremum character of S. So how do we do that? Okay, let us take that. See, so x is not, and okay, what you want to prove that in that case x is not an upper bound of that. So let us see how we work on this. We choose an n such that 1 by n square is less than or equal to 1 by n. So this is what you want to prove. So let us see whether you can do this. Okay, you compute this x plus 1 by n whole square. So ultimately, you see the whole of analysis will boil down to some hard work of computations. This is x square plus 2x by n plus 1 by n square. Now, if you can get this one, this 1 by n square less than 1 by n, then you see that this is less than or equal to x square plus 2x by n plus 1 by n, and therefore you get this as, so you get 1 by n okay, so you can write this as, this is equal to x square plus 1 by n into 2x plus 1. Okay, so this is what you compute, this inequality you get. Now 2 minus x square is positive. 1 minus, okay, one plus 2x is positive. This comes from our assumption that we are assuming x square is less than 2. So this is assumption. And 1 plus 2x is obviously positive because x is taken as positive, therefore this is 2. So that is positive. Therefore, we can have 1 by n can be chosen such that this is less than 2 minus x square. We are using one of the theorems. This is a positive number, this is a positive number, therefore you can, what you have is that you have n into 2 minus x square is greater than 2x plus 1. This is positive. And from this you get this inequality. Therefore this is positive. Okay? Right? Therefore in that case what you get? You get x plus 1 by n whole square is less than or equal to x square plus 1 by n 2x plus 1 This is less than x square plus 2 minus x square, which is equal to 2. So you get x plus 1 by n is whole square, x plus 1 by n whole square is less than okay. Therefore, what you get? You get x plus 1 by n belongs to yes. That's what we wanted to prove. So, since x plus 1 by n belongs to yes, you see that x cannot be the supremum. Okay, so that's a contradiction. A similar, manipulation would give you the other result also, namely that one can prove, assume x square is greater than 2. I won't go into the proof. So assume x square is greater than 2. Then what you prove is the following. Prove that there exists m belonging to n such that x minus 1 by m is also an upper bound of S, which implies x is not the supremum of that works out. So that I leave it to you to work out. It's again a similar set of manipulation that gives the result. Okay. Now let me finally state. Okay. So therefore, what you call this is that x is designated by the positive square root of 2. So that x square equal to 2. This is the symbol. So the x is what is called the supremum of this particular set. Now, if you are familiar with what is called the concept of Dedekind cut, there also you are talking about sets of this kind, x square less than 2. Okay, and that introduces that's a cut by definition, and that cut settles everything. Okay, fine. So those who are familiar with the Dedekind cut can look into it and see that exactly we are doing the same thing, and we have used the assumption that the larger collection, that is Q, has been enriched with all these cuts so that you get R constructed with that. It's a beautiful construction in mathematics. I want you. Yes. Now there are two important results, proofs of which are fairly simple. Says that if x and y are two real numbers, such that x is less than y, then there exists a rational number R belonging to Q such that x is less than R less than y. What does this say? It says that if you take any two real numbers, in between you can squeeze in or you can find a rational number. Okay? And later we also assert that if you are given any two rational numbers, in between you can find an irrational number. So it is not alternatively, rationals and irrationals that you have, but what you have is a very curious distribution of these rationals and irrationals on the intervals. Okay, this in fact tells you that the set of rationals is dense in R. That is, set of that is why you call it completion. Okay, let us just look at the proof of this. Okay, proof. Assume X is positive. Now this is an assumption that is not required. We can always work. This is a sort of without loss of generality. So you have to say why it is without loss of generality. Now y minus x is positive. Therefore, there exists an n belonging to n such that 1 by n is less than y minus x. What is that? That's clear. Therefore, nx plus 1 is less than ny. That's the same as this. Okay. So now there exists an m belonging to n such that m minus 1, that's the one that I said earlier, less than or equal to nx less than n. Okay. Therefore you have, this implies what with this? M minus 1 plus 1 is nx plus 1. So you have n x is less than m, and m is less than m, and this is less than ny, because nx is less than ny plus 1. So you have added that, you have shifted everything here. So you get this. Therefore, you see that x is less than m by n less than 1. So that completes the proof of that. Okay. So this is a beautiful theorem. And now it is just one little stroke to prove the other way. Let me prove that. And then complete the whole thing. So between two real numbers, there is always a rational number. So also between two corollary, if x and y are numbers, are real numbers such that x less than y, then there exists an irrational number z such that okay. So we prove this. The proof is amazingly simple. You take x by square root of 2 and y by square root of 2. Then what you can do is, this is 2. Okay, and in between there is a rational number. Therefore, by the previous theorem, x by root 2 less than r less than y by root 2. So r is, this belongs to 2. So what does this imply? X less than r root 2 less than y. Now all that you have to prove is that if r is a rational and square root of R square root of 2 is not rational. Okay. So you get some amazing results using the what do you call it, assumption that the supremum all bounded subsets of real line have their supremum in all subsets bounded above. I think I stop with that. Thank you very much for this opportunity. Maybe I talked to you very long, but I hope you would follow it up with say Bartle and Sherbert. I have exclusively followed Bartle and Sherbert. You can see all the details there and spend some time sitting down and working it out in detail. I'm sure your analysis will be very, very strong. Thank you very much.
All the participants now get an opportunity to interact with Professor Krishna sir. You can interact in any language, not a problem. All of you, please ask your doubts. Also get advice from this great mathematician. Use this opportunity.
Thank you very much for that.
Sir, the session was very interesting and informative, sir.
Thank you.
Okay. And even the undergraduate students also can easily follow your lecture. The topic that you have engaged is part of their syllabus also.
Yeah. What I wanted to emphasize on was that this is a stage, especially the undergraduate students. They are not familiar with proving theorems. In fact, what they do normally is do some manipulation, do some computations, and finally get a result. But the mathematics is not that. Mathematics starts with examples. In fact, a rich collection of examples analyzed will suggest a mathematical result. And then you try to prove it. You have to prove this from, because many of the things that we have proved here look almost trivial, because you know rational numbers, you know real numbers. So all these inequalities that we have proved here almost look trivial. You might ask, why should you prove it at all? That's not the case. If it is to be acceptable in mathematics, it has to go through the rich or rigorous, regulations of a proof for the result. It's not verification. Verification is not the proof in mathematics. For instance, given a two irrational numbers, you can always just verify and put a number in between once the two numbers are given. But the question is, can you do it always? So that is resolved only if you give a proof free from what is called those specific features of the numbers. Okay. So the first and important foremost thing that you should realize is that a proof is required. The second point is that, mathematics is like very similar to playing the game of chess. It is subject to very rigid rules and regulations. Now, in the game of chess, you all know, you have a board consisting of 64 squares, alternately what you call black and white, and then there are 32 pieces, and you are fighting out a battle. And each piece has its own movement. This is specified. You cannot, tamper with that. These are the rules of the game which you can never violate. Okay, I'll give you a very interesting example. Now, suppose you know nothing about chess, but you watch two people playing the game. Then you realize that there is a piece which they call the bishop. Okay, right? There are 4 bishops in the battlefield. Now, one thing that you observe is this. This is an observation that a bishop that was initially in the black square never enters a white square throughout the game. It stays in the black square only. This is an observation that you make. So you have a conjecture evolving from there. What is the conjecture? That a bishop in the black square always remain in the black square, not in the same square, but in some black square after any number of moves that you make on the board, because you are subject to certain regulations of movement of the bishop. Bishops can move only diagonally. That's a condition. Okay. So you make a conjecture, and then if you give a formal proof for this mathematically, then it becomes a theorem. So this is how theorems come out. So what I wanted to emphasize upon is that the observations in this case are essentially your experience on working with various examples, and that suggests certain general results or general patterns that you discover, which you write down as a conjecture. But if you just conjecture it, then you have to give a proof. That is why in mathematics there are many unsolved problems where the results appear to be very plausible, but people were not able to prove. Okay, there are a number of conjectures of this kind which could not be proved. For instance, a very simple thing. You know what are called twin primes. Okay, twin primes. What are the examples? Examples you have are 3 and 5. Then you have 5 and 7, and then you have 11 and 13, probably 17 and 19, then maybe 29 and 31, and so on. So twin primes are two primes which are separated only by one number in between. Okay, these are the primes. There are not many. How many of them are there? This is the question. How many such twin primes exist? This is a question. A very simple question that anybody would ask. Okay, you would ask a question. For instance, you ask, are the primes finite or infinite? Of course, you have an answer to that. You have given a proof. Okay, you have a number of proofs to prove that this is infinite. Primes are infinite. But what about twin primes? You can ask a similar question. Very legitimate. But the truth is that you still don't know. It's an open problem. Okay. Likewise, E is a transcendental number. Pi is a transcendental number. I am quoting from number theory mainly because it's very easy to state a problem. Okay. Then you ask, what is the status of E plus pi? Everyone thinks it is transcendental, but there is still no specific proof for this. Likewise, you can see that there are several conjectures that are open conjectures, and people are struggling to prove this theorem. Sometimes in the effort to prove such conjectures, a whole subject has evolved. A lot of other questions have sprung up and they have been answered. One such thing is, the so-called four-color conjecture, which was a very famous conjecture until 1977, when a sort of proof of this kind, this problem was suggested by few mathematicians, but using computers. So there were problems like whether such a proof should be accepted or not accepted, but at least now it has been accepted. So it is a four-color conjecture is now a theorem. But this problem remained open for such a long time, and a number of, and the whole entire graph theory owes very much to the to this particular question. because a lot of results in graph theory and new ideas in graph theory has evolved out of this, which may not be immediately connected to this, but you can see that it has come out by trying to answer this question. So that is what mathematics is all about. It's a very, very fantastic discipline, and if you can properly, what you call, just enter that and start enjoying what is happening there, then I think it's an incredible world.
Also, there is a continuous platform that we have just inaugurated. That is Krishna's classroom, and we will have a platform, Professor Learn from Professor V. Krishna Kumar, and that is a platform through Google Classroom in which the YouTube videos supporting materials and also a continuous interaction with the Professor Krishna Kumar sir through Google Meet will be available, so that those who haven't yet joined the program, please contact us and join the program at the earliest.
Hello, sir.
Okay.
Sir. Sir, വളരെ നല്ലൊരു ക്ലാസ് ആയിരുന്നു. കൂടുതൽ കാര്യങ്ങൾ മനസ്സിലാക്കാൻ പറ്റി. സർ, ഇതിന്റെ ഈ മേഖലയിലെ റിസർച്ച് ടോപ്പിക്കിനെ കുറിച്ചിട്ട് കുറച്ചുകൂടി കാര്യങ്ങൾ പറയാമോ?
ഞാൻ പറയാം. ഇത് ഇപ്പൊ ഈ ഏരിയയില് as such there is nothing left, but if you dig in, there may be some new information that are still to be resolved. But if you want, if some research problems are to be presented, then you need a lot of background to be brought in, and the involved sophisticated language that you use has to be learned, and your present job is to learn that language properly, so that you become more and more literate in mathematics. And there is a stage where you automatically, open problem will just come to your mind and then start working on them. But analysis is the basis of many areas in mathematics, like differential equations and so on, and which has something to do with nature, in the sense that many physical laws are formulated in terms of various equations, include differential and integral equations. So it will just automatically come there. Okay. So these are the fundamentals that you should really learn. Okay. Right.
Okay, sir. Dear participants, our IQAC coordinator, college IQAC coordinator, Pramod Kumar KV couldn't join with us due to some technical problems on the inaugural session. Now he is ready and he is now on our platform. I invite our colleague and IQAC coordinator, Sri Pramod Kumar KV sir, to this program and also to say a few words.
I'm sorry that I could not join all of you in time because of some technical error. And I just called Priyanka and told her that if possible, I will just join at the end of this program. But anyway, I like to congratulate the Fraternity of Mathematics Department for organizing such a brilliant session in the subject, possibly benefiting many of the mathematics lovers inside and outside our institution. And of course, we know that this pandemic time is really exerting so much stress on all of us, and how to transact knowledge in the proper way beyond the barrier of this kind of pandemic restrictions. That's always been a matter of a challenge. And how to encounter such challenges and to pay more attention to the possibilities of disseminating knowledge among the community is really an academic adventure. And let me tell sincerely that mathematics department has succumbed to this barrier and tried the best to disseminate the knowledge. And this ought to be a model and an encouragement to all the departments. And I hope in future, our departments all together will just organize this kind of the program to make more and more academic fervor among the community. And of course, as the person concerned with the college IQAC, I like to tell you that we are also just planning series of such talks from all the departments, and possibly in the nearest future, IQAC is trying to organize such a grand program, just inviting all the departments to make the plans of action. Possibly within a tenure of or a span of 5 or 6 days, all the departments will just make different types of seminars or webinars. Even the terminology nowadays has gone a tremendous change. All seminars are really being renamed as webinars. And anyway, we can't stop when problems are surrounding us. As the very enthusiastic learners and activists of this educational arena, we have to find always been some solutions to all the problems. And problem solving is not merely a problem of mathematics department, but it is the responsibility and the real task that everybody are entitled to embark upon when situations are really becoming much different and quite antagonistic. So I'm really thankful to the mathematics departments, our principal, and all the student community, and all the members who just tried to join with this great program, and of course the resource person who just opened the new arena of knowledge, shared his thoughts and knowledge with the students. I'm extremely thankful to all such people. And actually, I thought of speaking in Malayalam when I just joined this program, but Biju encouraged me to talk in English. So I'm sorry that I could have talked in Malayalam, but since we are all bilingual animals, nothing to worry about it. And again, I like to record my thanks to all of you again and again. Thank you very much, Biju, for your leadership, Priyanka, Orsis people, and the leadership of our principal, and the enthusiastic participations of everybody. Thank you very much.
Thank you very much, Pramod.
Thank you, sir. Thank you very much.
I want to say a few words. I mean, you mentioned about the pandemic and the challenges thrown in front of us by the pandemic. And I think yes, probably it had done something positive for me to go into this kind of, webinar mode. That is, rather than traveling to different places and speak yes, from my home. And I created all the necessary minimum infrastructure that in my house. That is one thing. And I think okay, Biju had been playing a very, very positive role in this way, because he is the person who was driving me to do this. Okay, and I have no words to express my gratitude to him. Thank you very much.
Sir. Okay. Thank you, sir. Everything is open to you. Let me just get away from this for a while, because I have some other online program very, very soon. So thank you very much, Biju. I'm leaving now.
The reason is that there are some participants from outside Kerala also in this group.
Of course, I know that's why I could not join with you in the beginning, because some technical limitations I can understand.
No problem. Okay, thank you for.
Thank you, sir. Thank you, Krishna, sir. Everybody, thank you very much.
Thank you.
Okay.
Hearty welcome to Divya Miss, HOD of Mathematics, SN College, Kannur.
Yeah.
Sir.
Yeah,
കൃഷ്ണകുമാർ
please.
സാർ ഓർക്കുന്നുണ്ടാവുമല്ലോ അല്ലെ എന്നെ?
ഉണ്ട്.
സാർ നമ്മുടെ വെബിനാറിൽ സാർ
ഉണ്ടായിരുന്നു.
സാർ വളരെ ഇൻഫോർമേറ്റീവ് ആയിരുന്നു ഈ ഒരു സെഷൻ. കുട്ടികൾക്ക് നമ്മളെ സംബന്ധിച്ചിടത്തോളം UG സ്റ്റുഡൻസ് മാത്രമേ ഉള്ളൂ SM കോളേജിൽ. നമ്മളെ UG സ്റ്റുഡൻസ്, ഫൈനൽ ഇയർ സ്റ്റുഡൻസ് മിക്കവാറും എല്ലാവരും തന്നെ യൂട്യൂബ് വീഡിയോ വാച്ച് ചെയ്യുന്നുണ്ടായിരുന്നു. കാരണം അവരുടെ സിലബസിലുള്ള ഒരു ഇതാണല്ലോ സുപ്രീമം ഇൻഫിമം എന്നുള്ളത്. അതുകൊണ്ട് അവര് വാച്ച് ചെയ്തിട്ടുണ്ട്. അവർക്കൊക്കെ വളരെ ഇഷ്ടപ്പെട്ടിട്ടുണ്ട്. അവര് മെസ്സേജ് ചെയ്തിട്ടുണ്ട് വളരെ നന്നായിരുന്നു എന്ന് പറഞ്ഞിട്ട്.
താങ്ക് യു വെരി മച്ച്. ഞാന് ഒരു മാസത്തിലൊരിക്കെങ്കിലും ഈ ഒരു പ്ലാറ്റ്ഫോമിൽ വരാൻ ഉദ്ദേശിക്കുന്നുണ്ട്, എന്തെങ്കിലുമൊക്കെ ആയിട്ട്. To keep this interaction live. അത് എനിക്ക് വിഷമമില്ലാത്തൊരു കാര്യമാണ്. പിന്നെ ഞാന് എന്റെ ആ ചാനലിൽ ഞാൻ റെഗുലറായിട്ട് പോസ്റ്റ് ചെയ്യുന്നുണ്ട്.
ഞാൻ സബ്സ്ക്രൈബ് ചെയ്തിട്ടുണ്ട്. എനിക്ക് നോട്ടിഫിക്കേഷൻ വരലുണ്ട്. അതുകൊണ്ട് ഞാൻ സ്റ്റുഡൻസിനും അത് ഷെയർ ചെയ്യലുണ്ട്. സ്റ്റുഡൻസ് അവരും സബ്സ്ക്രൈബ് ചെയ്തിട്ടുണ്ട് സാറിന്റെ ചാനല്.
അപ്പൊ അത് പരമാവധി ഉപയോഗിക്കാൻ അതില് കുറേയൊന്നും ആയിട്ടില്ല. ഇപ്പൊ ഏതാണ്ട് 36-37 ഒക്കെ അപ്ലോഡ് ചെയ്തിട്ടുണ്ട്. പൈപ്പ് ലൈൻ. അപ്പൊ അത് പരമാവധി കുട്ടികൾ ഉപയോഗിക്കാം. ഒരേ സമയത്ത് എനിക്ക് ഒരുപാട് കാര്യങ്ങൾ ചെയ്യാൻ പറ്റില്ല, പക്ഷെ ഇങ്ങനെ ചെയ്തു പോകണം. എനിക്കൊരു വലിയ ലോങ് ടേം പ്ലാൻ എന്ന് പറഞ്ഞാൽ as long as I can be effective, I will continue to post some lectures on that, which may be of use to the students. I mean, essentially, I want to leave for the students to learn something, and if they are interested from this particular source. So I have a perception of mathematics. Now I want to communicate that to the younger generation. That is the whole objective of that particular channel. So try to bring as many students as possible on that particular platform so that they can learn something.
Okay, sir. നമുക്ക് 6th സെമസ്റ്ററിൽ റീമാൻ ഇന്റഗ്രേഷൻ വരുന്നുണ്ട്. സാറിന്റെ കുറെ വീഡിയോസ് ഞാൻ കണ്ടു. അപ്പൊ
ഏതാണ്ട് എല്ലാം ഞാൻ ചെയ്തു കഴിഞ്ഞു.
അപ്പൊ 6th സെം തുടങ്ങുന്ന സമയത്ത് അതുകൂടി ചേർത്ത് വേണം എടുക്കാന്ന് വിചാരിച്ചിട്ടാണ് ഞാൻ ഇരിക്കുന്നത്. ഇപ്പൊ സാറിന്റെ ആ വീഡിയോസും ഒക്കെ ചേർത്ത്.
തീർച്ചയായിട്ടും. താങ്ക് യു വെരി മച്ച്.
താങ്ക് യു സർ.
Thank you, Miss.
Yes, my name is I'm Abhinav Sharma. I'm actually from RI Mysore. I'm actually in second year now, MSc in Mathematics.
Yes.
So yeah, this session was actually very good. I loved the way sir has explained all the topics from beginning to end. It was easier. It was very easy to understand it. Sir, if you don't mind, I would like to it's my personal interest in Pell equation actually. I would like to know your views on it. Actually, I have read Walter Rudin.
Yeah.
Actually, he has.
Which one? Rudin has written several books.
Yeah, Principles of Mathematical Analysis.
That is the baby Rudin, what people call baby Rudin.
Yeah.
This has been the text for analysis all over the world for quite some time.
Yeah, yes, sir. Actually,
before my books came. It's a beautiful book.
Yes, sir.
Except for some portions which I don't like, but otherwise, it's good. Very good book.
Yes, sir. Actually, in the starting, first chapter, real and complex number system. It is almost the same thing. You started with that piece that like p square is equal to 2, and if we do the contradiction.
That's right.
Sir.
Yeah.
After that, he has actually told about. He has made an equation. If A is a set of all positive rational numbers P such that P square is less than 2, and let B consist of all positive. Yeah, that equation.
That is exactly what I did here.
Yes, sir. But
because here I straight away worked in a space where the supremum property holds. But otherwise, what happens is you start with Q. When you have only Q in your hand, you start with such sets like x square less than 2. The set of all x belonging to Q with x square less than 2. And then what you do is you use that as a cut on the set of rational numbers, and then include all the possible cuts of this kind and enhance the system to a larger one. And on that you can extend your addition, multiplication, and then order relation, everything there consistently, and that gives you the real number R.
Yeah.
And R is a new system where you have, the additional advantage that every bounded set has a supremum and an infimum.
Okay.
So that is what you call the completion of Q into R.
Yes, sir.
And there are many different ways in which you do the completion. One mode of doing it is through what is called Cauchy sequences. And why do you want to complete Q? Because if you take a Cauchy sequence, which is what you call a convergible sequence, you will see that sometimes the limit won't exist inside that system, like Q. You can construct a sequence like, from the exponential series, you can construct a sequence of rational numbers which converge, which are convergible in the sense that the sequences are Cauchy, but it doesn't converge to a rational number, it converges to E. So you have to bring in such elements also. So that is one route through which you do the completion. And they are all the same. I mean, all these things are the same.
Thank you, sir.
You can look into the book by Hewitt and Stromberg.
Sir, once again,
Abstract analysis. I think it is called a real and abstract analysis or something like that. Hewitt and Stromberg. That's the author. It's a beautiful book on analysis. Yeah.
Okay, sir. Thank you, sir.
So you are from RCE?
RI, the Regional Institute of Education.
Sir,
Yeah.
That changed.
he is a
Student of Madhu.
Yes, sir.
Madhu is your teacher.
Yes, sir. Yes, sir.
Yeah. Madhu was my student, yes. Yeah. Okay, thank you for your interest.
Yes, sir.
hello, dear Abhinav Sharma. Have you joined for the continuous lecture series program?
Yes, sir.
Okay, so that you will have more chance to interact with the Krishna Kumar sir.
Yes, sir.
Okay, so your interaction was very important. Okay, okay, thank you.
Sir,
Yeah, for you.
എനിക്കൊരു ഡൗട്ട് ഉണ്ട്. അത് ഇപ്പൊ നമ്മൾ ആറിലൊരു സബ്സെറ്റ് എടുക്കുന്ന അതിന് ലിമിറ്റ് പോയിന്റ് എക്സിസ്റ്റ് ചെയ്യുന്നുണ്ട്. അങ്ങനെയാണെങ്കിൽ നമ്മുടെ ഈ സുപ്രീമോ ഇൻഫിമം എന്ന് പറയുന്നത് അതിന്റെ ഡിറൈവ്ഡ് സെറ്റ് തന്നെ ബിലോങ് ചെയ്യും.
നിങ്ങൾ എന്താ ഒരു സബ്സെറ്റ് എടുക്കണോ, അതിന്റെ ലിമിറ്റ് പോയിന്റ്സ് ഉണ്ട്,
അതിന്റെ ലിമിറ്റ് എക്സിസ്റ്റ് ചെയ്യുന്നുണ്ട്. അങ്ങനെയാണെങ്കിൽ അതിന്റെ സുപ്രീമോ ഇൻഫിമോ ഇതിന്റെ ഡിറൈവ്ഡ് സെറ്റിൽ തന്നെ ഈ ലിമിറ്റ് പോയിന്റ്സ് തന്നെ ആയിരിക്കുമോന്ന്, ഏതെങ്കിലും ഒരു ലിമിറ്റ് പോയിന്റ് ആയിരിക്കുമോ?
ഡിറൈവ്ഡ് സെറ്റ് എന്ന് പറയുന്നോണ്ട് ഉദ്ദേശിച്ചത് നിങ്ങള്
അതായത് നമ്മുടെ സെറ്റ് ഓഫ് ലിമിറ്റ് പോയിന്റ്സിലെ ഒരു പോയിന്റ് ആയിരിക്കുമോ സുപ്രീമോ ഇൻഫിമോ?
അത് ഇതൊരു ലിമിറ്റ് പോയിന്റ് ആയിട്ടാണല്ലോ വരുന്നത്.
ഡൗട്ട് ചെറിയ
അതെ, അത് നമ്മള് ഇപ്പൊ എടുക്കുമ്പോ ഈ സുപ്രീമം ഇൻഫിമം കൊണ്ടുവരുന്നതിന്റെ റാഷണൽ നമ്പേഴ്സിലെ ഈ ലിമിറ്റ് പോയിന്റ്സ് ഒക്കെ ഇൻക്ലൂഡ് ചെയ്യാൻ വേണ്ടിയിട്ടാണ്. മനസ്സിലായോ? കാരണം റാഷണൽ നമ്പേഴ്സിൽ കുറെ ഗ്യാപ്സ് ഉണ്ട്, ആ ഗ്യാപ്സ് ഫില്ല് ചെയ്യാൻ വേണ്ടിയിട്ടാണ്. അപ്പൊ അതൊക്കെ ഏതാണ്ട് ഈ റാഷണൽസിന്റെ ഇപ്പൊ ഞാൻ പ്രൂവ് ചെയ്തില്ലേ, ഈ ലാസ്റ്റില് പ്രൂവ് ചെയ്ത ഭാഗല്ലേ, സെറ്റ് ഓഫ് റാഷണൽസ് ആർ ഡെൻസ് ഇൻ റിയൽസ്. അപ്പൊ അതിന്റെ ലിമിറ്റ് പോയിന്റ് ആയിട്ടാണ് ഇപ്പൊ മറ്റുള്ള പോയിന്റ്സ് ഒക്കെ വരിക, ആ ഇറാഷണൽസ് ഒക്കെ വരിക.
ഓക്കെ സർ, താങ്ക് യു.
സർ നേരത്തെ കട്ട്സിനെ കുറിച്ച് പറഞ്ഞിട്ടുണ്ടായിരുന്നില്ലേ, റാഷണൽ നമ്പേഴ്സിനെ. അത് ഡെഡിക്കിൻ കട്ടാണോ? അത്
ഡെഡിക്കിൻ കട്ടാ ഞാൻ ഉദ്ദേശിച്ചത്.
ആണോ? അതിനെ പറ്റി, ഡെഡിക്കിൻ കട്ട്സ് വഴിയുള്ള റിയൽ നമ്പേഴ്സിന്റെ കൺസ്ട്രക്ഷനെ പറ്റി ഒന്ന് എന്താ പറയാ, ഒന്ന് ചുരുക്കി പറയാൻ പറ്റുമോ?
ഞാൻ ഇതെന്താ ചെയ്യണ വെച്ചാൽ റിയൽ ലൈൻ എടുത്തിട്ട് അതില് യു കൺസീവ് എവറി പോയിന്റ് ആസ് എ കട്ട്. കട്ട് എന്ന് പറഞ്ഞിട്ടുണ്ടെങ്കിൽ ആ ഒരു വരയുടെ പിന്നിലുള്ള എലിമെന്റ്സ് ഒക്കെ ഉള്ള ഒരു സെറ്റ്. മനസ്സിലായേ? അപ്പൊ എക്സ് സ്ക്വയർ ക്യൂ എടുക്കുക, ക്യൂ എന്നാണല്ലോ തുടങ്ങുന്നത്. ക്യൂ എടുക്കുക. അപ്പൊ നമുക്ക് നമ്മുടെ കയ്യിൽ 6 ഇല്ല, ക്യൂ ആണ് എടുക്കുന്നത്. അതിനെല്ലാം ഒരു ലൈനിന്റെ മുകളിൽ നമ്മള് പ്ലോട്ട് ചെയ്ത് കഴിഞ്ഞു. പ്ലോട്ട് ചെയ്ത് കഴിഞ്ഞാല് നമ്മള് വാട്ട് വി ഡിസ്കവേർഡ് ദാറ്റ് ദർ ആർ സം ഗ്യാപ്സ് ഉണ്ടെന്നാണ്. ആ ഗ്യാപ്പും കൂടി ഉൾപ്പെടുത്താൻ വേണ്ടിയിട്ട് എന്താ ചെയ്യുന്നത് വെച്ചാല് ഒരു സെറ്റ് എടുക്കാം. ഫോർ എക്സാമ്പിൾ, യു ടേക്ക് ഓൾ പോയിന്റ്സ് എക്സ് ബിലോങ്ങിങ് ടു ക്യൂ സച്ച് ദാറ്റ് എക്സ് ഇസ് ലെസ് ദാൻ 1 എടുത്തു വിചാരിക്കാം. അപ്പൊ അത് ഡിഫൈൻ ചെയ്യുന്ന റിയൽ നമ്പർ അല്ലെങ്കിൽ ആ കട്ടിനെ ഒരു 1 എന്നുള്ള റിയൽ നമ്പർ ആയിട്ട് നമ്മൾ ഐഡന്റിഫൈ ചെയ്യണം. ഇതിലെ പ്രോബ്ലം എന്താണെന്ന് വെച്ചാല് ഇപ്പൊ എക്സ് സ്ക്വയർ ലെസ് ദാൻ 2 എന്നുള്ളത് അതും ഒരു കട്ടിനുള്ള ക്വാളിഫൈ ചെയ്യുന്ന ഒരു സെറ്റ് ആയിരിക്കും. അപ്പൊ വാട്ട് ഈസ് ദ നമ്പർ കറസ്പോണ്ടിങ് ടു ദാറ്റ്? ദർ ഇസ് നോ റാഷണൽ നമ്പർ കറസ്പോണ്ടിങ് ടു ഇറ്റ്. Therefore you introduce it as a new number. You call it real number. അപ്പൊ അങ്ങനെ എടുത്തിട്ട് ഈ റാഷണൽ നമ്പറിനെ എടുത്തിട്ട് അതിൽ കട്ട് ചെയ്തിട്ട് എല്ലാ പോയിന്റും കട്ട് ചെയ്യാണ് ചെയ്യുന്നത്. അപ്പോ പുതിയ നമ്പേഴ്സ് എമർജ് ചെയ്യും, പുതിയ പോയിന്റ്സ് എമർജ് ചെയ്യും. റാഷണൽ നമ്പേഴ്സ് മാത്രമല്ല, അല്ലാത്ത ഈ റിയൽ ലൈനിൽ എന്താ ഉള്ളത് നമുക്ക് അറിയില്ലല്ലോ. റാഷണൽസ് എല്ലാം പ്ലോട്ട് ചെയ്ത് കഴിഞ്ഞു. അപ്പൊ ആ ഗ്യാപ്പ് വല്ലതും ഉണ്ടെങ്കിൽ അതൊക്കെ കിട്ടാൻ വേണ്ടിയിട്ട് ഇതിനൊരു പുതിയ വിധത്തിൽ കാണുകയാണ് ചെയ്യുന്നത്.
ഓക്കെ സർ. അപ്പൊ ഇങ്ങനത്തെ സെറ്റ് തിയററ്റിക്കൽ ആയിട്ടുള്ള അപ്രോച്ചുകൾ അങ്ങനെ വായിക്കാൻ പറ്റിയ ബുക്ക്, അതായത്
ഇത് വളരെ വളരെ ഏർലി അപ്രോച്ചാണ് ഇതിനോടുള്ളത്. ഡെഡിക്കിൻ കട്ട് എന്ന് പറയുന്നത് അത് റാഷണൽ നിന്ന് അടുത്ത ലെവലിലേക്ക് പോകുമ്പോ ഇതുപോലുള്ള പ്രോബ്ലം ഒരുപാട് കാലം they were just worried about, like square root of 2 is not there, pi is not there, e is not there. ഇതൊക്കെ പ്രൂവ് ചെയ്യാനും വളരെ ബുദ്ധിമുട്ടിയിട്ടാണ് അതെല്ലാം പ്രൂവ് ചെയ്യുന്നത് പലതും. പക്ഷേ they are not rational numbers എന്നുള്ളത് ക്ലിയർ ആയിരുന്നു. അപ്പോ then how do you get this? അപ്പൊ പക്ഷെ അതിനൊക്കെ ഇപ്പൊ ഉദാഹരണമായിട്ട് സ്ക്വയർ റൂട്ട് ഓഫ് 2 ഒരു ലൈനില് ആ പോയിന്റ് കണ്ടുപിടിക്കാൻ ബുദ്ധിമുട്ടൊന്നുമില്ല. കാരണം ഒരു റൈറ്റ് ആംഗിൾ ട്രയാങ്കിളിന്റെ യൂണിറ്റ് സൈഡുള്ള റൈറ്റ് ആംഗിൾ ട്രയാങ്കിളിന്റെ ഹൈപ്പോട്ടന്യൂസിന്റെ ലെങ്ത് സ്ക്വയർ റൂട്ട് ഓഫ് 2 ആണ് അല്ലെ? അതിനെ നമുക്ക് ഒരു റൂളർ ആൻഡ് കോമ്പസ് ഉപയോഗിച്ചിട്ട് ആ പോയിന്റ് ഈ ലൈനിൽ മാർക്ക് ചെയ്യാൻ പറ്റും. There's a geometric construction that you can easily do. അത് ഫൈനൈറ്റ് നമ്പർ ഓഫ് സ്റ്റെപ്സിലുള്ള കൺസ്ട്രക്ഷൻ തന്നെയാണ്. അപ്പൊ റൂട്ട് 2നെ കൺസ്ട്രക്ട് ചെയ്യാൻ പറ്റും. പക്ഷെ അത് അങ്ങനെ ഒരു റാഷണൽ നമ്പർ ഇല്ല എന്നുള്ളതാണ് പ്രശ്നം. അപ്പൊ അത് എന്താണെന്നുള്ള ചോദ്യം വരുമ്പോഴാണ് ഈ ആറിൽ നിറച്ചും ഹോൾസ് ആണെന്നുള്ളത് റിയലൈസ് ചെയ്യുന്നത്. അങ്ങനെ ആ ഹോൾസിനെ മുഴുവൻ ഫില്ല് ചെയ്യാൻ വേണ്ടിയിട്ടുള്ള ഒരു ഐഡിയ ആണ് ഈ കട്ട് ഉപയോഗിച്ചിട്ട് ചെയ്യുന്നത്. അപ്പൊ എല്ലാ പോയിന്റിലും 6 എടുത്തിട്ട് എല്ലാ പോയിന്റിലും ഓരോ കട്ട് ഉണ്ടാക്കാൻ പറ്റും. അപ്പൊ കട്ടിന് കറസ്പോണ്ടിങ് ആയിട്ട് സെറ്റ് ഉണ്ടാവും. ആ സെറ്റിന് കറസ്പോണ്ടിങ് ആയിട്ട് ഒരു നമ്പർ ഡെസിഗ്നേറ്റ് ചെയ്യും. അപ്പൊ കട്ട് ഡിഫൈൻ ചെയ്ത് കഴിഞ്ഞാല് കട്ട് തമ്മിലുള്ള അഡീഷൻ, കട്ട് തമ്മിലുള്ള മൾട്ടിപ്ലിക്കേഷൻ, കട്ട് തമ്മിലുള്ള ഓർഡർ റിലേഷൻ, ഇതൊക്കെ ഡിഫൈൻ ചെയ്യാൻ പറ്റും. അപ്പൊ ഇതെങ്ങനെയാ ചെയ്യണമെന്ന് വെച്ചാൽ ഇപ്പൊ റാഷണൽ നമ്പേഴ്സിന്റെ സെറ്റ് എടുത്തു, അതിലൊരു കട്ട് ഡിഫൈൻ ചെയ്തു. കട്ട് ഡിഫൈൻ ചെയ്ത് കഴിഞ്ഞാല് ദേ ആർ സബ്സെറ്റ്സ് ഓഫ് ആർ വിത്ത് സർട്ടൻ സ്പെസിഫിക് പ്രോപ്പർട്ടീസ്. മനസ്സിലായോ? ക്യൂലെ അത് സോ വാട്ട് യു ഹാവ് എ ന്യൂ a collection of subsets of Q are now available. അതിനെ നമ്മള് ആ സെറ്റില് നമുക്ക് അഡീഷൻ ഡിഫൈൻ ചെയ്യാൻ പറ്റും, മൾട്ടിപ്ലിക്കേഷൻ ഡിഫൈൻ ചെയ്യാൻ പറ്റും. രണ്ട് കട്ട് എടുത്തിട്ട് ആഡ് ചെയ്താൽ യു വിൽ ഗെറ്റ് അനദർ കട്ട് എന്ന് പ്രൂവ് ചെയ്യണം. അതുപോലെ രണ്ട് കട്ട് എടുത്തിട്ട് മൾട്ടിപ്ലൈ ചെയ്താല് യു വിൽ ഗെറ്റ് അനദർ കട്ട്. അത് ഞാൻ സിമ്പിൾ ആയിട്ട് പറഞ്ഞതാണ്. സപ്പോസ് എക്സ്, set of all x which is less than r, so set of all x which is less than p ആണെന്ന് വിചാരിക്കുക. അപ്പൊ ഈ രണ്ട് സെറ്റ് എടുക്കാന്ന് വിചാരിക്കുക. അത് ദാറ്റ് കറസ്പോണ്ട്സ് ടു ആർ ആൻഡ് പി എന്നുള്ള നമ്പേഴ്സിനായിട്ട് ബന്ധപ്പെട്ടതാണ് അല്ലേ? അപ്പൊ അങ്ങനെയാണെങ്കിൽ ആർ പി എന്നുള്ളത് എങ്ങനെ കിട്ടുക? ദ സെറ്റ് ഓഫ് ഓൾ elements z equal to xy, where x belongs to the first set and y belongs to the second set. And you have to prove that it is a cut. Adur cut aanengil endha sambhavikkana? It is again a element of the same class. Pinne ningal ee paranja property ningalku prove cheyan pattum. Adoru mathematical endha paraya idayitte valare deep aayittu cheyavunna oru karyമാണ്.
Okay, sir.
Well, addition, multiplication, order relation. This മൂന്ന് ചെയ്യാൻ പറ്റും. അപ്പൊ രണ്ട് x, set of all x less than p, set of all x less than q. ഇങ്ങനെ രണ്ട് കട്ട് ഉണ്ടായിരിക്കുക. So p is less than if the first cut, the set corresponding to the first cut is contained in the set corresponding to the second cut. മനസ്സിലായോ? Less than q. അങ്ങനെയാണ് order relation define ചെയ്യുക. പിന്നെ നിങ്ങൾ പ്രൂവ് ചെയ്യുന്നത് എന്താണെന്ന് വെച്ചാൽ എല്ലാ റാഷണൽ നമ്പറിനും കറസ്പോണ്ടിങ് ആയിട്ട് ഒരു കട്ടുണ്ട്. പക്ഷേ ഈ റാഷണൽ നമ്പറിന് കറസ്പോണ്ടിങ് അല്ലാത്ത കട്ടുകളും ഉണ്ട്. ആ കട്ടുകളാണ് നിങ്ങൾക്ക് ഈ റിയലിലേക്ക് എത്തിക്കുന്നത്. മനസ്സിലായോ? അതൊരു ആ ഒരു ഫിലോസഫി നിങ്ങൾ ശരിക്കും മനസ്സിലാക്കണം.
പിന്നെ ഇത് നമ്മള് കാൻഡേഴ്സ് കൺസ്ട്രക്ഷൻ പറയില്ലേ, കോശി സീക്വൻസിന്റെ കംപ്ലീറ്റ്നെസ് വെച്ചിട്ട്, കോശി സീക്വൻസ് അതായത് ക്യൂവിലെ കോശി സീക്വൻസുകളുടെ ലിമിറ്റ് പോയിന്റ്സും കൂടെ
അത് ചെയ്യാം, അങ്ങനെ ചെയ്യാം, അങ്ങനെയും ചെയ്യുന്നുണ്ട്. ദാറ്റ് ഇസ് അനദർ വേ ഓഫ് കൺസ്ട്രക്ടിങ്. അത് ഒരു തവണ ഈ പ്രോബ്ലം റിസോൾവ് ചെയ്ത് കഴിഞ്ഞപ്പോ there were many ways in which you could do it, because then you realize that these are all after all limit points. അപ്പൊ ലിമിറ്റ് പോയിന്റ്സ് അതിലില്ലാത്ത ലിമിറ്റ് പോയിന്റ്സ് ഒക്കെ നിങ്ങൾ അതിന്റെ അകത്തേക്ക് കൂട്ടിയെടുക്കുകയാണ് ചെയ്യുന്നത്. അങ്ങനെയാണ് ഈ കാൻഡസെറ്റ് അല്ല എന്താ പറയാ, കാൻഡസെറ്റ് അല്ല എന്താ പറയാ, കോഷി സീക്വൻസ് കൺസ്ട്രക്ഷൻ വരുന്നത്. പിന്നെ അതിന്റെ വളരെ ജനറലൈസേഷൻസ് ഉണ്ട്. ഇഫ് യു ഹാവ് എനി മെട്രിക് സ്പേസ് യു ക്യാൻ ഹാവ് എ കംപ്ലീഷൻ. ഇൻ പർട്ടിക്കുലർ വെൻ യു ടേക്ക് യു ഇറ്റ് ഹാസ് എ കംപ്ലീഷൻ ടു ആർ. അത് ആറാണ്. So for any metric space it has a completion. അത് വളരെ അബ്സ്ട്രാക്ട് ആയിട്ട് പ്രൂവ് ചെയ്യാൻ പറ്റും. പക്ഷെ അത് എന്താണെന്ന് ചില കേസിൽ ഓബ്വിയസ് ഒന്നുമല്ല. അങ്ങനെയൊക്കെയുള്ള ഫങ്ഷനാലിറ്റീസ് ഒക്കെ ചെയ്യുമ്പോൾ അത് കാണാൻ പറ്റും.
The material on Dedican cuts by Professor Kumar sir is available on the title on the real line. There is a 18 videos are there already uploaded in the Krishna's Classroom YouTube channel.
Okay, sir.
Okay, in that videos you can see.
Okay, sir. Thank you.
Okay, thank you.
There's a beautiful book by Hardy, G.H. Hardy. It's called Pure Mathematics. പഴയ ബുക്കാണ്, ക്ലാസിക് ആണ്. അതില് നല്ല മനോഹരമായിട്ട് ചെയ്തിട്ടുണ്ട് ഇതൊക്കെ.
ആ ബുക്കിന്റെ പേരൊന്നും കൂടെ പറയോ?
പ്യൂർ മാത്തമാറ്റിക്സ് ബൈ G.H. Hardy. അത് നെറ്റിൽ കിട്ടും, കാരണം അത് വളരെ പഴക്കമുള്ള ബുക്കാണ്. You can download that book. It's a beautiful book. G.H. Hardy. ഹാർഡിയെ പറ്റി കേട്ടിട്ടുണ്ടായിരിക്കല്ലോ അല്ലേ? രാമാനുജൻ.
Okay, sir. Thank you.
Okay.
I invite Professor Major Jacinta Miss, please.
Good afternoon.
Yes.
ബിജു ആയിട്ടുള്ള കണക്ഷൻ, അതുപോലെ ഇരിട്ടി കോളേജുമായിട്ടുള്ള കണക്ഷനിൽ ഇതിനു മുമ്പ് തന്നെ ബിജു ചെയ്തതും അതുപോലെ കുമാർ സാർ ചെയ്തതുമായിട്ടുള്ള എല്ലാ വീഡിയോസും ഞാൻ കാണുന്നുണ്ട്. സാറിന്റെ ക്ലാസ് വളരെ ഇൻട്രസ്റ്റിംഗ് ആയിട്ട് എനിക്ക് സാറിന്റെ ക്ലാസ്സിൽ ഇരിക്കാനുള്ള യോഗം ഓറിയന്റേഷൻ കോഴ്സ് കാലിക്കറ്റ് യൂണിവേഴ്സിറ്റി നടത്തിയപ്പോൾ 91 ഐ തിങ്ക് ഞാൻ ജോയിൻ ചെയ്തിരുന്നു. സാറിന്റെ ക്ലാസ് ഞാൻ കേട്ടിട്ടുണ്ട്. ആ ഒരു ഓർമ്മയിൽ വിജു പറയുമ്പോഴെല്ലാം ഞാൻ സാറിന്റെ ക്ലാസ് എനിക്ക് ഇതിനു മുമ്പ് തന്നെ ആ ലിങ്ക് അയച്ചപ്പോൾ തന്നെ ഞാനത് ഓരോ തവണയും കേൾക്കുകയും എന്റെ സ്റ്റുഡൻസിന് ഇപ്പൊ ഞാൻ ഒരു സെൽഫ് ഫിനാൻസിംഗ് കൂടെ വർക്ക് ചെയ്യുന്നുണ്ട്. എന്റെ എല്ലാ സ്റ്റുഡൻസിനെയും ഞാൻ ജോയിൻ ചെയ്തിട്ടുണ്ട്. ഫൈനൽ ഇയർ സ്റ്റുഡൻസിനെ, സെക്കൻഡ് ഇയേഴ്സ് കുറെ പേര് ജോയിൻ ചെയ്തിട്ടുണ്ട്. അപ്പൊ ഇങ്ങനെയുള്ള ക്ലാസ്സുകൾ കേൾക്കാൻ അവർക്കും ഞങ്ങൾക്കൊക്കെ കഴിയാത്തത് അവർക്ക് കഴിയട്ടെ എന്നൊരു ഇങ്ങനൊരു അവസരം കിട്ടിയതുകൊണ്ട്, ഇത് ഓൺലൈൻ ആയതുകൊണ്ടാണ്. സാധാരണ പോലെ കോളേജ് ഇപ്പൊ ഓപ്പണിംഗ് ആയിരുന്നെങ്കിൽ ഇങ്ങനെയുള്ള അവസരം കിട്ടില്ലായിരുന്നു. ഇങ്ങനെയുള്ള അവസരം ഉണ്ടായതിന് അത് ഓരോരുത്തരും നല്ലത് തന്നെ. അപ്പൊ ഇങ്ങനെയുള്ള അവസരങ്ങള് സാറിന് ഇതുപോലെ ക്ലാസ് എടുക്കാനുള്ള ഒരു തോന്നലും ഒക്കെ ഉണ്ടായതിൽ സാറിന് ഒരുപാട് നന്ദി പറയുന്നു. ഓക്കെ, താങ്ക് യു സർ.
ജസീന മിസ് ഞങ്ങളുടെ എല്ലാ പ്രോഗ്രാമിലും വളരെ നല്ല സപ്പോർട്ട് നൽകുന്നതാണ്. ജസീന മിസ് സർ സയ്യിദ് കോളേജിൽ മാത്തമാറ്റിക്സിന്റെ ഹെഡ് ഓഫ് ദി ഡിപ്പാർട്ട്മെന്റ് ആയിരുന്നു. ഇപ്പോഴും പിലാത്തറ സെന്റ് ജോസഫ്സ് കോളേജിൽ വർക്ക് ചെയ്യുന്നു. Just Madhu has joined in this group from RI. Madhu, Mr. Madhu.
Yeah, actually yes. I have shared the link to my students, but what happened, unfortunately, in my home there was a power problem was there in the there, so I missed one big portion of that class, and I was in YouTube also. I think, sir, that day that you might. It might be missed. I might have missed some portion. The square root. You start with square root of 2. That square root of 2. That it is not a rational number. Later we come to completeness. Sir, how to prove that it is, whether it is discussed or not? I'm not able to. Whether we discussed that whether root 2, existence of root 2 using. Yeah,
we have discussed it.
Okay. That is the one
we part I said that see, x square, you go to R where the Supremum property is there.
Yeah.
Okay. Then once it is Supremum property is there, you look at the set of all x for which x square is less than 2. I mean all positive numbers x with this property. Adine Supremum because you prove that it is bounded, therefore bounded. It is a supremum.
Non-empty bounded.
ആ സുപ്രീമം നിങ്ങൾക്ക് ആണ് ഈ പ്രത്യേക നമ്പർ വിത്ത് ദ പ്രോപ്പർട്ടി ദാറ്റ് ഇറ്റ് സ്ക്വയർ ഈസ് ഈക്വൽ ടു 2. അപ്പൊ അത് അത് 3 പോസിബിലിറ്റി ഉള്ളത്. ആ സുപ്രീമം നമ്പർ അപ്പൊ അതിനെ y എന്ന് വിചാരിക്കാം, y എന്ന് വിളിക്കുക. അങ്ങനെ y ആണെങ്കിൽ y square equal to 2, y square is less than 2, y square is greater than 2. ഇങ്ങനെ 3 പോസിബിലിറ്റി ആണുള്ളത്. മനസ്സിലായോ? അപ്പൊ അതിൽ നമ്മൾ ആ മറ്റ് 2 പ്രോപ്പർട്ടി റൂൾ ഔട്ട് ചെയ്യാം. സോ ദാറ്റ് y square is equal to 2. Therefore, that is clear. ഞാൻ പറഞ്ഞു.
സർ ഇത്
ഇറ്റ്സ് വെരി നൈസ്.
സർ ഇത്
വെരി ഇൻട്രസ്റ്റിംഗ്.
സർ ഈ മെത്തേഡ് നമുക്ക് സാധാരണ ഇപ്പോ എക്സിസ്റ്റൻസ് ഓഫ് nth റൂട്ടുകൾക്കൊക്കെ ഇത് തന്നെയല്ലേ മെത്തേഡ്? ഈ പ്രൊസീജിയർ തന്നെയല്ലേ?
അതെ. nth റൂട്ടിനും ഒക്കെ ഉപയോഗിക്കുന്നത് അതാണ്. പക്ഷെ അത് കുറെ കൂടി കമ്പ്യൂട്ടേഷണലി ഇറ്റ് വിൽ ബി മോർ സോഫിസ്റ്റിക്കേറ്റഡ്.
ഈ കൺസ്ട്രക്റ്റബിൾ അല്ലാത്ത നമ്പേഴ്സ്, അതായത് ഇപ്പോ ഉദാഹരണത്തിന് പൈ, ഈ തരം നമ്പറുകളെ എക്സിസ്റ്റൻസ് കാണിക്കാൻ എന്താ ചെയ്യേണ്ടി വരിക? നമുക്കിപ്പോ പൈയുടെയും ഈയുടെയൊക്കെ എക്സിസ്റ്റൻസ് വേണമെന്ന് വെച്ച് കഴിഞ്ഞാൽ അവിടെ നമ്മള് കോഷി സീക്വൻസ് ആണോ ഉപയോഗിക്കുന്നത്? ഇപ്പൊ മറ്റേ മാഡം ചോദിച്ചു
കൺവേർജ് ചെയ്യുന്നതാണ്.
കാരണം വെച്ചാൽ ഇത് ഡിസ്കസ് ചെയ്ത് വരുമ്പോ നമ്മൾ റൂട്ട് വെച്ചിട്ട് പറയാറുണ്ട്. പിന്നെ
അതിന് കംപ്ലീറ്റ്നെസ് പറഞ്ഞാൽ പിന്നെ അതായി എല്ലാ കോഷി സീക്വൻസും കൺവേർജ് ചെയ്യുന്നതാണ് പിന്നെ അതിൽ ഒബ്സർവ് ചെയ്യുന്ന ഒരു കാര്യം. ആൻഡ് once you have that completion, then you are assured that any sequence of rational numbers which is Cauchy has a limit. And that is unique also. അങ്ങനെയുള്ള നമ്പേഴ്സിനെയാണ് പൈ എന്നൊക്കെ പറഞ്ഞിട്ട് വിളിക്കുന്നത്. പൈ എന്നൊക്കെ പറയുന്നത്.
അപ്പൊ ആ രീതിയിൽ ആ കംപ്ലീറ്റ്നെസ് തന്നെ നമുക്ക് ഉപയോഗിക്കാം അവിടെ, അല്ലെ? അതിന്
അതെ, അതാണ് ഇവിടെ ഇതിലെ ഏറ്റവും ഒടുവിൽ ഞാൻ പ്രൂവ് ചെയ്ത് എന്താന്ന് വെച്ചാല് between any two real numbers there is a rational number. and between any two real numbers, there is also an irrational number. Actually, eventually you have proved the density of rational numbers in reals.
Reals. Yeah.
ഒരു റിയൽ നമ്പർ എടുത്തിട്ട് ഒരു നൈബർഹുഡ് എടുത്തിട്ടുണ്ടെങ്കിൽ അതിലൊരു റാഷണൽ നമ്പർ ഉണ്ടായിരിക്കും.
Yeah. Sir, I have just received some messages from my students also. They are telling it was very much useful for them, especially some students of class means 11. Some students have messaged me. They have actually completed that their analysis course, and actually they are studying topology. So they have told it was very much useful for them. Lecture.
A good understanding of real line will help them to go to metric spaces and then to topological spaces.
Topological spaces.
Thank you, sir.
Thank you, sir. It was very much helpful for everyone, also for me also, because even if I miss some part
today on the video, it's a long time.
Yeah. Okay, sir. Okay, sir. I will.
Okay, fine.
You can take. I will be here only. Yeah.
Thank you, Madhu sir. Please cooperate with us in the future program, continuous lecture program.
Surely.
Okay.
Okay.
I am very happy to see that some of your students have already joined in the program.
Okay. Yeah. I have shared. Actually, it was little late because yesterday I have told them that there will be session will be there, but time I was telling them 10:30.
Yeah.
Suddenly message come. I also did not see that immediately. That is why some of them could not watch in Google Classroom. But I think many of them have joined in the YouTube streaming.
Okay. Moreover, your student, Mr. Abhinav Sharma, interacted with Kumar sir.
Yeah. He's a third semester student. He's studying analysis for the first time.
Yeah.
But he's very, very good, and he start exploring Rudin and other things, books present now itself, even though their textbook is Bertil.
Yeah. Okay, he asked some area regarding Rudin also.
Okay, yeah. Okay.
Okay, thank you, sir. Sri Lakshmi, MP.
Sir, നല്ല ക്ലാസ് സാറിന്
അറിയാം.
അപ്പൊ നല്ല ക്ലാസ് ആയിരുന്നു. നമുക്ക് പഠിക്കാനുണ്ട് ഇത്. നമുക്ക് അത് ഒന്നുകൂടി നന്നായിട്ട് നല്ല ഡീറ്റെയിൽ ആയിട്ട് പറയുമ്പം കുറച്ചുകൂടി നന്നായിട്ട് മനസ്സിലാവുന്നുണ്ട്. ഭയങ്കര യൂസ്ഫുൾ ആയിരുന്നു ക്ലാസ്.
ഇനി ആ പുസ്തകം വെച്ചിട്ട് വർക്ക് ചെയ്യണം.
ഓക്കെ സർ.
അതിലത്തെ എക്സാമ്പിൾസ് ഒക്കെ ട്രൈ ചെയ്ത് നോക്കണം. കാരണം പ്രോബ്ലം ചെയ്യാണ്ട് മാത്തമാറ്റിക്സ് പഠിക്കാൻ പറ്റില്ല. കാരണം ഈ സ്കില്ലാണല്ലോ നിങ്ങൾ ഡെവലപ്പ് ചെയ്യേണ്ടത്. ആർട്ട് ഓഫ് ഡൂയിങ്
നന്നായി മനസ്സിലായി കഴിഞ്ഞാൽ പിന്നെ നമുക്ക് പ്രോബ്ലം ചെയ്യാൻ കുറച്ചുകൂടി എളുപ്പം ഉണ്ടാവല്ലോ. അപ്പം ബേസ് നന്നായി തന്നിട്ടുണ്ട് സാർ.
അത് ഡെവലപ്പ് ചെയ്യണമെങ്കിൽ പ്രോബ്ലം അറ്റംപ്റ്റ് ചെയ്തിട്ടേ ഉണ്ടാക്കാൻ പറ്റുള്ളൂ. അത് ഏതാണ്ട് നമ്മള് വെള്ളത്തിലിറങ്ങിയാലേ നീന്താൻ പഠിക്കാൻ പറ്റുള്ളൂ എന്ന് പറയുന്ന മാതിരിയാണ്. പ്രോബ്ലംസ് ചെയ്യുക അല്ലാണ്ട് വേറെ യാതൊരു മാർഗവുമില്ല മാത്തമാറ്റിക്സ് പഠിക്കാൻ. അപ്പൊ ഓരോ പ്രോബ്ലം ചെയ്യുമ്പോഴും ചെറിയ ചില പ്രശ്നങ്ങൾ ഉണ്ടാവും. ആ പ്രശ്നങ്ങൾ ഉണ്ടാവുമ്പോഴൊക്കെ നിങ്ങൾ യു ലേൺ സംതിങ് ന്യൂ. അപ്പൊ ഒരിക്കലും ഒരു പ്രോബ്ലം ഉണ്ടായി എന്ന് വെച്ചിട്ട് ഒരു പ്രശ്നത്തിൽ ഉണ്ടായി എന്ന് വെച്ചിട്ട് അത് അവിടെ വെച്ച് ഒഴിവാക്കരുത്. ആ പ്രോബ്ലം റിസോൾവ് ചെയ്യാൻ
പഠിക്കുള്ളൂ നമ്മള്. ഓക്കെ സർ.
ഹസീന മിസ്.
സർ താങ്ക് യു സർ.
കട്ടിലവെപ്പൊക്കെ കഴിഞ്ഞോ?
ഫുഡ് കഴിഞ്ഞു, കട്ടിലവെപ്പ് കഴിഞ്ഞു.
അത് നന്നായി. ഇറ്റ്സ് എ ഗുഡ് പ്രോഗ്രസ്.
സൗണ്ട് ആണ് ഇവിടെ, അതുകൊണ്ട് ക്ലിയർ ആവുന്നില്ല. ഓക്കെ സർ.
സർ
പറയൂ.
സർ നല്ല സെഷൻ ആയിരുന്നു സർ. ഞാൻ ഫുൾ ടൈം കണ്ടോണ്ടിരുന്നിട്ടുണ്ടായിരുന്നു. താങ്ക് യു സർ, ഒരുപാട് താങ്ക്സ്.
ഓക്കെ, താങ്ക് യു.
ഓക്കെ സർ.
സർ നല്ല ക്ലാസ് ആയിരുന്നു. കുറെ മനസ്സിലാക്കാൻ പറ്റി സാർ. പിന്നെ KSOMന്റെ പരിപാടിയില് ഞാൻ ഉണ്ടായിരുന്നു. അപ്പൊ സാറിന്റെ കുറെ ക്ലാസ് ഒക്കെ അവിടെ നിന്നും കേൾക്കാൻ പറ്റിയിരുന്നു.
ശരി.
താങ്ക് യു സർ.
ശരി, ഓക്കെ, താങ്ക്സ്.
ഹലോ സാർ.
പറയൂ.
ഞാൻ സാറിന്റെ ക്ലാസ് ഫോളോ ചെയ്യാറുണ്ട് യൂട്യൂബില്. അപ്പൊ ഒരുപാട് ഹെൽപ്ഫുൾ ആണ്. ഈ ക്ലാസ്സും നന്നായിരുന്നു സാർ. ബേസിക് ഒക്കെ നന്നായിട്ട് എടുത്തോണ്ട് വളരെ നന്നായിട്ട് മനസ്സിലാക്കാൻ പറ്റി. താങ്ക് യു സാർ, താങ്ക് യു സോ മച്ച്. ബിജു സാറിന് ഒരുപാട് നന്ദി പറയുന്നു ഇങ്ങനെ ഒരു സെക്ഷൻ നമുക്ക് വേണ്ടി. താങ്ക് യു സാർ, താങ്ക് യു സോ മച്ച്.
Anusha dear.
ഹലോ സർ.
പറയൂ
സർ. ക്ലാസ് നല്ലൊരു ക്ലാസ് ആയിരുന്നു. നല്ല രീതിയിൽ മനസ്സിലാക്കാനൊക്കെ പറ്റി. ബേസ് ഒക്കെ ക്ലിയർ ആയിട്ട് തന്നെ മനസ്സിലായി. ഓക്കെ സർ, താങ്ക് യു സർ.
ഓക്കെ.
ജോമിഷ.
സർ, ഭയങ്കര നല്ല ക്ലാസ് ആയിരുന്നു. എല്ലാം നല്ലപോലെ മനസ്സിലാവുകയൊക്കെ ചെയ്തു സർ.
ശരി, താങ്ക്സ്.
Okay, dear participants, let us wind up this session now because Professor Krishna sir is engaging and already busy with for the last 3.5 hours because he was ready by 9:30 a.m. and now it is around more than 1 p.m. We couldn't give him a cup of tea also, even a cup of tea for during this.
I'll make my own tea.
Okay, sir. Okay.
I'll make my own tea. Okay.
Okay, sir.
Anyway, I'm going
also,
for lunch now.
Yeah. And also, all the participants really cooperated with us, continuously listening for the last 3 hours. I appreciate each one of you for being with us, and also continue your support and learn good mathematics from eminent persons like Professor Krishna sir. And Department of Mathematics is engaging a continuous program with the guidance and support from Professor Krishna sir. All of you are invited to join the program so that let us move and learn together so that the next generation also will be get benefited, and all the students who are members of this group also will be benefited, and also they will get an opportunity to relearn mathematics also. I invite my student, MSc student, Mr. Anisha, to say vote of thanks.
Good afternoon all. It gives me immense pleasure to deliver vote of thanks for this event to all dignitaries assembled here. We are all blessed to have a lecture by eminent mathematician Professor V. Krishna sir, and it is also very lucky to be a part of this online lecture series titled Learn from Professor V. Krishna sir. And today's session was very informative and we all enjoyed very much. Thank you so much, sir. Let me do my duty of proposing vote of thanks. First of all, I would like to thank our chief guest, Professor V. Krishna sir, on behalf of all the participants of this program. And he's doing a great job to encourage all of us by sharing his precious time. Thank you so much, sir. And I would like to thank our principal, Dr. Ajita teacher of our college. Thank you so much, teacher, to inaugurate this function. And I would like to thank Mr. Kumar KV, our IQAC coordinator, who presided over this function. Thank you, sir. And I would like to thank our beloved HOD of Mathematics Department, Dr. Bijimon sir, and all other teachers, Hazina teacher, Jimli Miss, my teacher, and Vidya teacher, and Priyanka teacher, who take the initiative to conduct such a wonderful program. Thank you so much, all teachers. And I also express my sincere gratitude to all the participants, and I hoping that we will meet in the upcoming lecture series. And thank you once again to all. Thank you so much, sir.
Okay, thank you.
Thank you, Anisha. I request Krishna sir to conclude the session.
Okay, thank you very much for this opportunity. I will be coming back again with some new topic sometime. And okay, meanwhile, I'll also put lot of things on my channel, and I think some of them should be very of interest to you. Thank you very much.